What if you could make your car battery last much longer and have a more predictable start, even with a weaker battery, all with a simple upgrade? That's exactly what super capacitors can do. Today I'll show you what really happens when we connect them in parallel with the battery, why balancing is critical, and how LEDs can help us to monitor it. Let's dive in. Hello, I am Norbert, energy engineer, and I help do-it-yourself energy enthusiasts to take control of their energy needs. Today we continue the series on supercapacitors for various applications, and for now we focus on starting a car together with its normal battery. And sorry for the delay with this video. I had some serious problems with time. For example, I purchased an affordable 6-pack capacitor module with 6 of these capacitors, and they were mounted on this circuit board with all the components with the balancing circuit. It didn't work as expected. The voltages on the capacitors were very uneven and only one LED was lit up. And then dismounting this 6-pack and testing the individual capacitors showed that they were performing surprisingly well and stayed nearly equal in voltage. So I was again happy that I purchased them after the initial disappointment. And the result? After seeing that this balancing system was inefficient and after looking for alternatives for other standalone boards or also complete packs with the capacitors which were first-class material, they were too costly or they had long delivery times. Well, I just had to select an alternative and waiting for the delivery. What happens when we connect them? In an earlier video I introduced the concept of using supercapacitors to support the car battery. Today we will explore the real-world effects when starting a car engine and the importance of balancing capacitors when they are connected in series. How a simple diode and LED setup helps to see the health of the capacitor. Here below is the circuit with the supercapacitor and the protection. Then above you have the car battery, alternator and the users, inclusive the starting motor. What is happening inside the system? When starting, there will be a strong current for a few seconds. Let's say that it is a cold start for 3 seconds with 500 ampere, which is then 1500 ampere seconds, also expressed as 1500 coulombs. In reality, the first half second will be most intensive. But let's be conservative. The supercapacitors with their 500 farad and 1500 coulombs will be discharged by 3 volts. If they were first at 12.5 volt together with the battery, they will now be at 9.5 volt. This is normal, even with a new battery. With a normal battery and about 10 milliohms of internal resistance of the battery, the voltage drop will be 5 and not 3 volts. Well, that's exactly why you like this video, of course. After the start, with the engine running, 2 things will happen. The battery will recover the voltage difference between itself and a capacitor bank with a pretty high current. 3 volt divided by the internal resistance of the battery and 6 supercapacitors in series. So let's say 10 plus 6 milliohms. And then we will have nearly 200 amperes running inside the tool and right after the start motor is at rest. But it goes quickly down as the capacitor banks get at the same voltage as the battery. The whole process might finish in 10 seconds or so, and you can start again without stressing the battery as you did in the past. The alternator is now running and it will recharge the combination of battery with the supercapacitors. In the beginning, as the alternator voltage is the highest of the three, of the alternator, the battery and the supercapacitor, it might contribute with a nasty high current. That's because the internal resistance of the supercapacitor is really very low. It would be good to have a resistance in series of about 5 volt divided by 100 ampere or 50 milliohms between the alternator and the battery plus the supercapacitor. And by the way, because of this low internal resistance of the supercapacitor, it is very good that the battery or the alternator never must charge a completely discharged supercapacitor. In less than a minute, everything is in the steady state again, and the alternator will just give the current which is required by the various consumers in the car. Why is balancing essential? When capacitors are connected in series, small variations in leakage and also the farad values can cause individual voltage differences. If left unchecked, one capacitor may get overcharged and fail prematurely. If that is a short circuit, you get a domino effect and maybe firework. Yes, in your car. The solution is passive balancing using diodes, including light-emitting diodes or LEDs, and that's a simple, effective and also visible way to ensure stability. Is a series resistor necessary? Well, my answer is no. I see it many times in the systems, but I don't know exactly why. Charlie! A fuse can protect a failing diode that becomes a short circuit and which would cause a domino effect with the other diodes, but then the protection will not be active anymore and the whole supercapacitor is at risk. A well-chosen combination of normal and Schottky diodes ensures that the voltage stays below the 2.7 volt limit per capacitor, and the lower voltages of the Schottky diodes will allow you to be pretty precise. And a LED can help to monitor the voltage. In the prototype of today, I have instead the LED that is taking the whole deviation current, because this current is less here. Since car alternators can sometimes give 15 volts, which is not good, the LEDs can help to see this. They will then glow brightly, all the 6 of them. The total maximum voltage allowed on the capacitor bank is 16.2 volts, well above this 15 volts. Why is balancing essential? Understanding the diode's role in balancing. Think of the diode's current flow like a waterfall. Doubling the water height or the voltage exponentially increases also the water flow, in this case our electric current. I chose a combination of diodes that only conducts when needed, suppressing too high capacitor voltages very much. And don't worry about the high currents in the diodes. Even the max voltage of the capacitor, which is 2.7 volt, would not be able to cause a too high current in the diodes. I will demonstrate that in the experiment in this video. Before I show the several experiments and how I built the prototype capacitor bank, do you know why it is so difficult to make videos while developing a solution? Because I need to record this conversation and then cut the recording to make the explanation short and fluent. That takes many hours, and I must do it before I finish the experiments even. So it's always a surprise what I am able to show in the last minute. That's why I put often a few minutes of footage of my work near the end of the video, which might contain last minute recordings and not described in this conversation. This time I put it all at the end of the video, not only to have the audience until the end of the video. And that's very usual. YouTubers will ask you to look to the end of the video. But this time it is also for practical reasons and to avoid cutting in the middle of the video. At the time of writing this script, I expect to have eventually a prototype of the car booster at a small scale, which can still be used for pretty high currents of some 12-volt devices like an air compressor to inflate your tires, or a cool box of 40 watt. Also, the battery is much smaller, but anyway of 12 volts. By the way, it is 7 ampere hours, and that is 7 times 3600 seconds, so we are above 25,000 coulomb, much more than those 1500 coulombs which we calculated is necessary for starting. It would really be interesting to see if the Toyota RAV4 can start with this small battery. So I thank you for your understanding that there is not yet a full-scale car battery booster and protector. With all the above remarks and what I learned this week, you understand that I need to search for quite some special components if I want to realize a system for the real tough world. Also, big companies need time to make things that work, are safe, and if possible compact and good looking. They have a much bigger budget than me, so I hope that you will help me grow. Then I can dedicate more time to this creative job that fills me with energy. Sharing this video is an excellent way. Only you know how many of your friends would benefit from my videos. I hope that you too like to try, to invent and enjoy to make something that is really useful. Let's also show the big decision makers that we normal folks have plenty of imagination to know what's good for us and for the others around us. Let's save the planet and ensure that we have energy when we need it, even if things are not working well around us. Please like, share and subscribe with notification so that you won't miss any video. I want to help you to be an emancipated user, keeper in the sense of storage and producer of energy. Now let's see how LEDs can help us to see what's going on inside this otherwise black box. Choosing the right LEDs for voltage indication. LEDs are also diodes and act here as visual indicator of voltage imbalance. Finding low voltage, high power LEDs was challenging, so I might not use them in a final system to take the full deviated current. But in the prototype of today I will do, as you see here. So you see here the LED, it is burning now, and it is going afterwards through a diode. Applying thermal paste to the LED and sticking behind it aluminium foil is a very simple way to improve LED cooling if you want. It's maybe relevant if I find a LED that will take the full deviated current of at least 1% of the total current in the capacitors. Maybe you can advise me where I can find those LEDs which can conduct, for example, 2 or 3 ampere. Maybe you will say me that I have to dismount a big LED floodlight and then take the single LEDs. I don't know, I didn't find them singularly on Amazon. A possible enhancement is that you use traffic light style indication, so yellow and red. They both have the different voltages but low voltage. So red and yellow are both about 2.0, 2.4 volt. And other colors have a higher voltage that go beyond the voltage that are practical for this 2.7 volt. That would be nice to do it in the final version. Now let's see what I did this week. So this is a start situation, and we have now different voltages. This one, that is 159, and number 2 is 160, and you see indeed these two lamps are a little bit lit on. You can see them in the dark. This 136 and its LED is out. This 123, that's also too little, and here it is out. 142 is also not lit, and here's another high one because I see it's lit. It's the best lit. But anyway, you see that there are differences. These 4 and 5, they have less voltage, and also this one, 136, 123, and 142. And now we will apply a voltage. The total voltage is now 884, so that would be like a battery which is very discharged. We'll also take the battery here now. So here are the contacts of the battery. And the battery is 12.76. So I would not discharge this battery, which is not so strong, it is 7 ampere hours, on this super capacitor with a voltage of not even 9 volts. But we will now put a power supply on it. And what I will do is I will put it on the voltage of the battery. That's the better choice. 12.7, okay. And now I will connect it. Here's the power supply. And the other pole, the plus. I see now 3 amperes. And the voltage is increasing. Now it's 10 volt already. And 1 ampere. You see already that there are 2 LEDs lit. The 3 and the 5 is now also visible. And now also the 4 is becoming visible. So you see that this is consuming much, so much current is deviated. Anyway, we saw already that even with the 2.7 volt, this LED will not burn, and it will never come there. The total voltage is already 12.7, and now it's going on constant on the left of this power supply. That's constant voltage, so the current is quickly going down from 1 ampere less than 100 milliamperes. So in a bit of time all these lamps should be evenly lit. Now we will read the voltage, the individual voltages. This number 1, 222, 224. Well, that was already in the beginning, they were equal. 202, 187. So this is the weakest one. 206, 225. So it's clear that the voltage of this power supply is always 12.7, because that is just simulating the regulator of the car, of the alternator. So that will stay the same. But if this voltage here, the weak voltage, must go up 187, it should also go to the others. Then of course these strong ones, they must go down, otherwise you will never get the sum equal to the power supply. And remember that in a car this circuit is constantly on the battery, so there's plenty of time that the voltages become equal to each other. And once the voltages are equal to each other, then it's also easier to stay the same, if at least the super capacitors are equal. And for my initial measurements, which you will remember from the table, these super capacitors are more or less the same. And thanks to the characteristics of the diodes, which really starts to work well and to deviate much current at high voltages, as we come closer to the dangerous voltage of 2.7, they will become really active and even out every difference. This is the weak one. It's now 189. The first one is already less, 2.21. So they are all at 2 volt or more, unless this one, the number 4. But anyway, what we see is that the power supply is giving only a very little current. And that means the battery, which is at this voltage of the power supply, we can now connect it to this super capacitor, because with this voltage it will have to do very little. We will do that now. Now you see here the milliampere. It was very low. After an hour or so, it seems all the same. Let's measure. The current is 13.6 milliampere, and the voltages are 2.1, 2.1, 2.1, and number 4 is 2.08, 2.1, and 2.1. I will now put the alternator on, so it will be on charge. I will start to charge it at 14 volts. That's something that this battery can have. And then it should just stay the same. The same voltage for each. Ampere meter is not good. I will switch it. Because this meter is not working, we just put this now on the current meter, and this is the voltage meter. And it's now indicating 20 milliamperes. The power supply, I have it at 14 volts, so that would be the alternator of the car, and it goes to this battery. So it goes now to 1.2 ampere. The lights are still the same. I will now measure the voltages, the individual voltages. 2.17, it was first 2.1, 218, 220, 220, 219, 220. Then number 5 is 223, and we had 223 also for number 6. So that's pretty much the same. The power supply, so that's the alternator, that's 800 milliampere. But the capacitors, they take only half of that. So half of it is of the alternator's current is going into the battery and half of it in the capacitors. So okay, now we take alternator off and the total voltage is 13.7 still. It's going down a little bit, but anyway, let's see. Still the voltage is 227, 226, 225, 223, 225, 223. Let's take number 1 again. 225. So I have the impression that they are nearly equal, all the capacitors. What we can do now is that we will go into consumption. So let's simulate the starting engine. Now we have this little compressor. It's working on 12 volt and it is for compressing your tires. And I saw on the power supply that it takes 3.5 ampere in idling when there's no back pressure. And when I give a little bit back pressure with my finger, it goes to 5-6 amperes. We have now here the compressor, so that would be the starting motor, which you can hear but you cannot see it. You have here the voltage meter of the battery and also of the capacitors, of course. This current from the battery to the capacitors. So if it's negative, it's on 10 amperes, so it's here the decimal point. If it is negative, then it means that there is going current from the capacitor to the battery. And of course, because the current for the compressor is taken from these poles of the battery, it means that, of course, the battery, the capacitor will give the current and the rest of the current will come from the battery. So and now the current goes again to the capacitor. So it's 280 milliamperes going to the capacitor. So that means that the capacitor should have less voltage than the battery. Otherwise the battery would never do this. And that's of course because the battery went down more than the capacitor during the compression. And that means that the battery was going lower and the capacitor was keeping up the voltage. And now during operation you saw that it was below 12 volt. And now it's again going back because a battery is a complex chemical system that recovers itself a little bit after a minute or so. And here's the current which is still going from the battery to the capacitor. And okay, that has been an exchange. And now we will see if there's something changed in the voltages of the single capacitors. The LEDs seem equally bright, so that's already good. 2.07, 2.05, 2.06, 2.06, 2.06 and 2.06. So it seems indeed that every time that it is charging, that it goes better, because every charge is a possibility to have an input current to the capacitors, and input current means that that these LEDs are used through its equalization work. While once it is in equilibrium con the battery, And the current from the battery is like here. It's 40 milliampere, it's very little. And then nothing can be done about equalization, because if there's no current, there will also be no equalization. But from the other side, if we will now charge again, so we put the alternator, we put to work, and it's now on 14 volt. And that means there will go current to the battery and also the capacitor. So it's 2.7 ampere goes to the couple of them, and 1 ampere of which is going to the capacitor. So that means 1 ampere, which can, for every capacitor, it can go or to the diodes or to the capacitor. And of course the diodes will decide where it goes. And the beauty of the diodes is that if it comes close to the 2.7, then the diodes will start to conduct like crazy. So that means it will still more aggressively look that equalization is going on. Now the voltage is in total is of course 14 volt, because I read it on the power supply. The current is still 1.24 for the power supply, of which 0.4 is going to the capacitors and the rest goes to the batteries. So we have here a voltage of 227, 226, 227, 226, 227, 226. Well, that seems perfect. Well, more or less we did the experiment, we simulated everything that can go on in the car. The only thing is that we didn't take a very big current, because for this battery of 7 ampere hours, current which we took of about 5 ampere would be like 50 amperes for a normal battery, which is far from this 500 ampere which the cranking motor takes for starting the engine. But okay, we see that it seems that with every discharge and charge cycle, the equalization is going better, because every discharge and charge cycle is a current flowing into the combination of the capacitors and diodes, which for every capacitor is then an occasion to change to the right or the left in the capacitor or in the diodes, and so it's an occasion to correct itself. And regarding the resistance, which you could put in parallel to the diodes, I got a thought about that resistor could be interesting, because then also the discharge through the resistors can be an occasion to equalize and balance the voltages about on the capacitors. So that would mean that like the diodes, they will not conduct on return, on reverse. So the only way that you can discharge, that there can be an equalization, is through a resistance. And this resistance should of course be big, because otherwise you have discharge from the battery to those resistors. But anyway, it would mean that also during parking the car, the resistors would help in some way to equalize. But okay, it is still an energy loss, and a resistor that conducts so little that it would not be significant energy loss will also do, of course, less to the equalization. And anyway, the resistors are not so active, so they are proportional. So that means if a capacitor is a little bit different in voltage than the other, then there will be a little bit more or less equalization current that is deviated through that resistor. So I think that if you use a car regularly and you have this charge and discharge cycles, you don't need that time during parking the car to equalize. I think it can be done very well during the charging and discharging when the car is in use. Next steps and final thoughts. A full-scale car battery booster requires special high current components, including the current limiter resistance between the alternator and the battery, which is really an intervention in the car itself. Maybe someone of you can advise me. I would think of 50 milliohms, so that the alternator will not see a too low resistance if the super capacitor is there and it is discharged for a couple of volts. So in the next video, in this playlist at least, I will test this system on a real car. It's not mine, so I will be careful as if it were yours. I will be traveling to Rome next week. A full-fledged video will not be there, but I can update you on things that I find in the Eternal City, at least if they fit into this channel. Afterwards, I must fit in also a week for a heat pump assisted air exchange that I started last week, and viewers asked me to go into detail. I hope you will be there too. Fresh air is good for your health, and you want to be this air, not cold, fresh but not cold. See you in the next video.